I welcome you to this lecture on Generative AI-based visual field synthesizer for monitoring glaucoma progression. So we are submitting this for the second round of the Economic Times Hackathon. We from Tech University. Myself, Dr. C. Raja, Associate Professor from Department of ECE, and one of my students, Mr. Vishnu Sai from third year, Department of ECE. We are submitting this after clearing the first round. That is a basic qualifier and MCQ. So now we are going to discuss on what is Generative AI-based visual field synthesizer. Why visual field should be synthesized for monitoring glaucoma. So we are going to discuss on those points. Regarding the problem statement, we can say that glaucoma is the leading cause of blindness in the world. And the World Health Organization has stated that around 7.7 million people will be affected by glaucoma yearly. Okay. And glaucoma, regarding glaucoma, it is called as a silent thief of vision. Unlike cataract, where the damage can be initially itself tapped. But in glaucoma, till the patient comes to the later stage of the disease remains very silent. So that is why it is called as a silent killer of vision. And the manual diagnosis of glaucoma involves structural assessment and functional assessment. As we can see in the figure below, there is a structural assessment and functional assessment. The structural assessment is nothing but the doctors will see the fundus image or OCT image. So now we are strictly restricting to fundus. They see the structural changes in the fundus image corresponding to glaucoma or any disease. Whereas functional assessment is not something like making the patient sit and observe whether his visibility is clear or not. So this functional visual fields displayed as several values around the circle. They represent how the retina, how the eye of a particular person is sensitive to a particular light. So that is what is a visual field that is being taken. So standard automated perimetry is the device that is used to capture the visual field of a particular patient. Okay. So what is the easiness with what is the easiness with fundus and what is the difficulty with visual field? Let us discuss. And the for diagnosing diseases like glaucoma, both the structural analysis and functional analysis is very equally important. But looking about AI, artificial intelligence-based glaucoma diagnosis have been comfortably ignoring the visual field and the functional analysis. Only with the availability of fundus images, we have been doing the diagnosis of glaucoma with the structural analysis only. The AI-based diagnosis is restricted to that. So that's what it is given in one of the research papers. Due to the scarcity of open source multimodal glaucoma data sets. So why we need to go for multimodal apart from a very architecturally rich neural networks, multimodal takes close to reality. How the doctor diagnoses a disease and how the AI algorithms are diagnosing a particular disease. If I go and talk to a doctor saying that with the fundus image alone, I am going to diagnose glaucoma, he may not be fully convinced. Why? Because the functional analysis gives some details and the structural analysis gives some other details. Combining the details given in all the modalities, the doctor will be able to arrive at a conclusion. So that's what the next level of research we are going to build with the structural and functional analysis. With the availability of some data sets like GRAPE in recent times, there are 1,115 follow-up records from 263 eyes. So follow-up records in the sense this data set is also longitudinal. As of now, we are not going to longitudinal analysis. We are only restricting to the synthesis of visual field from fundus images. And of course, other secondary parameters also are there. We will see in detail what are all the data set description we will see. Okay. And more importantly, I want to tell about the difficulties in the acquisition of the visual fields. Several papers discuss about the difficulties in visual field acquisition, comparing the fundus imaging, even though the modality and the cost of the image is little higher compared to the visual field, the patient cooperation and the patient involvement in acquiring the visual field is very high. Okay, so that is what is given as the patient has to make a quick response, and particularly the people of old age affected by severe diseases like glaucoma, when they want to make a quick response, that makes the situation very tough. And several surveys are taken, and when the glaucoma patients are being made to talk, they have very particularly mentioned that taking the fundus image or OCT is not a much botheration, whereas the visual field acquisition has been a nightmare for the old patients. And the test variability is also there. Being a not much standardized procedure, there are also variabilities and it also consumes time. Okay. Whereas the acquisition of fundus images is going to take only a few 3 or 4 minutes, whereas the visual field acquisition is going to be a very laborious process for both the patient and also for doctors. So that's what with the availability, with the non-availability of data sets, we only restricted with the fundus images. But the task will be complete only if we integrate the multi-modalities, that is for image and also that visual field data. Okay, so that is what we have been discussing. And coming to the problem statement, so from the problem statement, we are going to the objectives to integrate functional assessment by visual fields into AI frameworks. So there are very, very little papers that concentrate on multimodality, taking fundus image and also visual fields, whereas most of the papers only concentrate on only one modality. It is not only on going for the next level of architecture, it is also about mimicking the manual diagnosis process. Okay. The second objective would be, of course, this is the main objective, to synthesize visual fields from fundus images with generative AI capacity. So that is what we are mainly going to do in this hackathon. We are going to synthesize the visual field values from fundus images. So there are grape dataset with grape dataset where fundus images and other secondary parameters are also there. Fundus images are there. So this is a particular folder containing the fundus images. For example, 1_OD_1 is the fundus picture. Corresponding to that fundus picture, the visual field values are given. As we have already discussed, what are visual fields? Visual fields are nothing but numerical values as shown on the right hand side, which represent the sensitivity of the human eye at each particular point. The doctors have several knowledge on the sensitivity is very less on a particular point or a group of points where the sensitivity is little less. So likewise, the glaucoma indicators are there with respect to visual fields also. So which we are going to train with AI. Okay, when the modalities are combined, the accuracy and the robustness of diagnosis will certainly increase. So that's what we are going to try in the project. As an initial pilot study, we are going to take the grape data set where the fundus images are there. And for each fundus, what are those in circle, the values were given no visual fields, so that are being flattened and it is being given. And of course several other secondary parameters are also there, like age, gender and all, it is there. So age is one of the important factors. So age correspondence will dictate, influence the presence of glaucoma or not. For example, fundus and visual field may be same similar for both the patients, whereas age is going to tell whether glaucoma is there or not. So, and we have the data set description also. What are all the different parameters available in this particular data set? And of course, the elaborate objectives from problem statement. I told the objectives. The elaborate objectives would be to develop a prototype app that synthesizes visual field from fundus images with a generative AI backend. We are going to develop an app with the AI, generative AI backend, to generate the following data sets from hospitals. So, as a later stage of this project, we are also going to generate data sets from hospitals in real time with combining fundus, visual fields, and intraocular pressure. And with the end of the hackathon, we are also trying to conduct the usability testing and user acceptance testing of the application. Okay, usability testing in the sense with the online data set, with the gold standard internet data set, whatever is available, whereas user acceptance testing will take it to real-time hospital testing. So we are planning to conduct that usability testing. So what will be the front end of the proposed app? The front end of the proposed app will be when you give the fundus image and some secondary data, it is already pre-trained as such with so many fundus images and secondary data. The output will be the visual field. So the generative AI algorithm will be able to generate the visual fields corresponding to a particular fundus image based on the learning. So regarding grape dataset, as we have already seen, and I want to talk about a few other works. This work 9, that is fundus. So this is one of the very few papers that have synthesized visual fields from fundus images, and they have taken a very primitive, not primitive, very AI algorithm ResNet 50 is being taken. This estimation models basic visual field synthesizers from fundus and the secondary parameters. So exactly whatever are available in the grape dataset, from the fundus and secondary parameters, they are evaluating the visual fields, and they are getting a mean absolute error of around 8 dB. So this paper doesn't work much on the AI algorithms, whereas they have very much worked on the creation of the dataset and the synthesis of visual field from, and they have made a primitive model. It's not a very much accurate model or a very high-end architectural model is not developed here. Only the introduction to The first model that synthesizes visual field from fundus image is being generated in this particular paper. Whereas coming to the second paper, it is little different. It is not a conditional GAN. That is, a paired data is not being synthesized. Take a paired data is used to train the GAN, generate AI, and one data is given, a second data will be synthesized. That is what is a conditional thing. Whereas this is not a conditional thing. The first one we have discussed, and the very objective of our work is also a conditional generative AI, where conditional means the paired data of fundus and the visual fields will be used to train the generative AI architecture. And at last, during the testing phase, when we give the fundus image alone, the visual fields will be synthesized. So that is what is the thing I wanted to say. Whereas the second paper is not just to understand about the very latest architectures being implemented in the generative AI. I studied this paper. So here we have a transformer. The advantage of the transformer is about its global learning, and so many other things are there. We will discuss shortly. And this transformer is used to handle the complex dependencies between the different columns of a particular tabular data. Using multi-head attention, it is able to do. That is what the accuracy of transformers is always very high compared to the CNNs. And coming to our work, what we are doing now, we are using vision transformers as encoder to CDPM, conditional diffusion probabilistic model. So the generative AI algorithm we are using here is the conditional diffusion probabilistic model. Conditional because we are using paired data and synthesizing one data from the other data for visual field synthesis. And vision transformers are used as a encoders to CDPM. And multi-layer perceptron is used for the secondary inputs. The other inputs like age, gender, even corneal thickness is also there. Several closely related biological parameters are also there. For those also we are using this MLP. Okay. And finally the tokens of all these AI models are fused at the output. So it is an extensive architecture. What is a novelty of the other things we have discussed already? So the first paper I told, the very single paper that worked on the synthesis of visual field from glaucoma. So that is a novelty. Real-time clinical data has been applied to synthesis. Whereas the second paper, it is using a very high architecture. So in fact, we are combining the advantages of both. We are deploying the very high architecturally novel neural network, and in fact making some enhancements in that also, and we are deputing that to the synthesis of visual fields from fundus images. And we have used a novel loss function, and we have used extensive architecture. In the second paper they have used only GAN. So compared to GAN, conditional diffusion probabilistic models are very advantageous. So we have used CDPMs in our work, and this is the overall block diagram of our work. So the fundus image one modality, imaging modality, and the secondary parameters, of course, age, gender, all those things are taken, and visual fields are also taken. Here, conditional embedding is done. For this particular fundus, this is the visual field. Likewise, conditional embedding is done, and that is given to the generative AI block. So this black box is a generative AI block, which is nothing but a conditional diffusion probabilistic model, which is a state-of-the-art generative AI block, and we are feeding the input to this. And finally, we will have the predicted visual fields. And this is the overall concept of our paper. And what are the advantages of vision transformers? I think the time is not sufficient to discuss on all those things. Whereas I wanted, in fact, to discuss on, elaborate on CDPMs and transformers also, but it's only a 2-minute video, I guess. And what are all the outputs we have got? We have taken the base model and the reliability weights, the weight modification done as per different layers. That is what is reliability weights. And we tested with the contrastive loss, and we can observe the mean absolute error is continuously decreasing with the different models. And all those models are being taken in our GitHub, whatever GitHub we have supplied, we have taken. Here we are calling the vision transformer model. And here mean absolute error will be given. Mean absolute error of 8 point it is given. So likewise, We have taken different architectures for training, contrastive loss, and the contrastive loss parameters we have optimized with the PSO, with which we further reduced the mean absolute error. Whereas comparing with the mean absolute error of the base paper, mean absolute error is 8 dB. We are still working on it. We are trying to put the transformers on this also. Instead of using multi-layer perceptron, we are trying to use transformers and doing some novelty in embedding those outputs also. Okay, so we expect the mean absolute error to increase further. And finally, what would be the front end of our application? Because the application we are going to debut to the hospitals, the generative AI backend will be there in this application, where the doctors will be able to attach any one fundus image and will be able to synthesize the visual fields. And the doctor perceivable visual field conversion will also be done. This is a very clean data set of visual fields, which has to be inferred by doctor, will be converted like this also. Okay. So we have several preliminary works also done in the several hackathons, and we have won several titles in IEEE international hackathons also. So maybe the time will not permit me to explain on all these things. So we have already developed apps on synthesis of OCTA, one image from another fundus image. Now this project is on visual fields. So the objectives of both the projects are totally different. So here image to image conversion, whereas in this new project we are trying to take fundus to visual field. And these are the references. And thanks for the attention.